Dr. Amanda Isaac, and my co-chair is Dr. Ibrahim El-Mogi. We have selected a very interesting program for today's AI session, which builds upon the AI courses that we started this year under the auspice of the Egyptian Society of AI in Healthcare. It gives me great pleasure to introduce the first speaker, Dr. Eleftherios Tzanis from the University of Heraklion in Crete. He's a medical physicist, and his work is focused on agentic AIs and AI in dosimetry. Hello.
Good afternoon, everyone. Thank you very much for your kind introduction. In this session, we will talk about large language models and agentic systems, and we will present a state-of-the-art multi-agent framework, Maestro, designed for end-to-end autonomous AI development in medical imaging. This is my disclosure. Let's start by understanding what agents are. Agents are built on large language models. They can understand human language and respond to it, but they can also use tools such as APIs or Python functions to interact with their environment and make changes to it. Commonly, agentic systems have four key components. First, we start with the large language model, which is basically the brain, the core reasoning engine of these systems. It decides which actions to take based on the situation and, of course, creates the necessary completions. Then we have the tools. These are what the agents use to interact with their environment. They can have access to databases and pre-processed data or develop machine learning models. Another key component is the system prompt. It's a set of permanent instructions that shape the behavior of these systems. The system prompt also includes valuable information regarding the specialized agents and the tools that the master agent has at its disposal. Of course, these systems have also memory capabilities, short or long-term memory based on the task. As large language models play a very important role in guiding these agentic systems, let's take a closer look at how these models work. So basically, LLMs excel at understanding and generating human language. They are built on transformer architecture, which is based on the attention mechanism introduced in 2018 by Google. The underlying principle of an LLM is simple yet highly effective. They simply need to predict the next token in a sequence of predefined tokens. We can think of a token as the unit of information that the LLM works with. A token may be a short word or a part of a word, as usually LLMs do not work with whole words. Once the text is split into tokens, each token is turned into an embedding vector, which is basically a unique number-based fingerprint. This fingerprint helps the model understand the meaning and context of each token. So basically, large language models work with numbers and not real words. Let's understand the next token prediction mechanism. LLMs are considered to be autoregressive. This means that the output of a previous pass is the input for the next one. This loop continues until the model predicts an end-of-sequence token. This is a special category of tokens, and when the model predicts one of those, it understands that it has to stop generating other words. But what really happens during a single decoding loop? Once the text is tokenized, the model calculates a representation that captures valuable information regarding each token and the position of each token in the sentence. Then the representation goes into the model, which outputs scores that rank the likelihood of each token in LLM's vocabulary as being the next token in the sequence. Large language models don't just generate responses randomly. Their behavior is guided by what we call system messages, also known as system prompts. These messages are not visible to the end user, but act as foundational instructions that shape how the model behaves in every interaction. Think of them as the model's underlying personality or operating mode. In this example, we have two identical tasks. Segment all visible organs in the provided CT scan. But the difference lies in the system prompt. On the left, the model is told to act as a professional medical imaging assistant, to be accurate, respectful, and efficient. And that is exactly how it behaves. On the right, however, the system prompt defines the model as a rebel assistant who doesn't follow instructions. The result? A completely different tone and behavior, despite the same user input. This illustrates how important system prompts are. They define not just what the model does, but how it does it. Agents work in a continuous cycle of thinking, acting, and observing. During the first step, thinking, the agent analyzes the user-defined task and devises a strategy on how to solve it. During the second step, the actions, specialized agents and tools are invoked based on the initial planning. During the last step, the observation phase, the agent either returns the results to the user, or if the task is not completed, or if this system observed an error, it initiates a new thinking, acting, and observing cycle. It is very interesting that these systems can detect their own mistakes and make corrections. Now that we understand the basics of large language models and agentic systems, let's see how all these come together in a real-world case. The Maestro project is our multi-agent system designed for end-to-end AI development in medical images. Everything starts with the master agent, Maestro, who communicates directly in natural language with the user. Users do not need to write any code. They simply describe the task and provide tabulated or imaging data, and then the master agent takes over. The master agent analyzes the task and devises a strategy on how to solve it. Then it distributes the work to a team of 8 specialized agents. The exploratory data analysis agent they are moving from here, but they do not show there.
السلايدز مش بتتحرك. I'm terribly sorry, we will fix it.
Wait. Okay. Wait. No. Yeah.
ممكن ترجعها تاني زي ما هي، تبتديها من الأول يعني، تقفلها وتفتحها تاني.
Let me get back to the right slide.
This one we didn't see.
Yeah.
Go back to the one before. The one before we didn't. Yeah.
So, okay, so agents work in a continuous cycle of thinking, acting, and observing. During the first step, the thinking, the agent analyzes the user-defined task and devises a strategy to solve it. During the second step, the action, specialized agents and tools are invoked following the initial planning. And during the observation step, the agent either returns the results to the user or initiates a new cycle of thinking, acting, and observing if the task is not completed yet. So, as I said earlier, the master agent analyzes the user-defined task and distributes the work to a team of 8 specialized agents. The exploratory data analysis agent performs descriptive analysis on input data. NNUNet and total segmentator agents handle segmentation tasks, while the radiomics feature extraction agent calculates quantitative features from anatomical images. Once data are pre-processed, other agents take over. The feature importance and selection agent picks the most relevant features, and then regressor agent, classifier agent, or image classifier agent develops based on the task the appropriate machine learning models. Then the master agent returns the results to the end user. This makes Maestro a powerful no-code framework where the user simply describes the problem and the agents build the solution. But I think it's better to understand Maestro through examples. In this complex task, the user asks Maestro to segment liver tumors for all MRI scans available in a predefined directory. After that, Maestro has to use these liver tumor masks along with the MRI scans to extract radiomic features and use these radiomic features as predictors to train an XGBoost classifier capable of distinguishing benign from malignant liver tumors. So the agent analyzes this task and first initiates the NNUNet implementer agent. This agent takes as input the anatomical MRI scan and automatically segments liver tumors. Once segmentation is performed for all the MRI scans, the NNUNet agent returns the results to the master agent. The master agent then invokes the radiomics feature extraction agent who calculates radiomic features and saves them as a CSV file. And lastly, the master agent initiates the classifier agent who uses the CSV with the radiomic features. It pre-processes the data and in minutes develops, evaluates, and deploys an XGBoost classifier capable of distinguishing benign from malignant liver tumors. In this second example, we will see how Maestro can minimize the needed time for the most time-consuming step in external beam radiotherapy, which is the manual delineation for the organs and tissues of interest. The user asks Maestro to segment various organs in a CT scan of a patient who will undergo external beam radiotherapy. The master agent invokes total segmentator. Total segmentator gets access to the CT scan and in less than 2 minutes segments all the requested organs. Then the agentic system returns the results to the clinical expert, and the clinical expert can review these segmentations, approve them, reject them, or make any necessary corrections before further processing. Maestro is fully open source and available on GitHub. In the GitHub repository, you will find detailed instructions on how to set up Maestro locally. We have made the process as simple as possible using Docker, so you can deploy the full framework on your own machine without worrying about dependencies or environment issues. And of course, you can use the fresh release, the Maestro desktop app. You can find instructions on how to download and deploy it locally in your machine by scanning this QR code. Also, these instructions are available on our GitHub page. And for those of you who will attend ECR, we will organize the AI contest there, and it will be based on Maestro. So this was the first part of my presentation, and now let's move on to the second part that we will discuss how we can perform a comprehensive evaluation of AI segmentation models that will be used in external beam radiotherapy. The traditional method for evaluating segmentation models is through metrics like dye similarity coefficient, Jacquard score, Hausdorff distance, and other similar metrics. However, the question is this evaluation enough for the domain of radiotherapy? For example, a dye similarity coefficient of 0.95 in terms of dose distribution, how can we translate it in terms of dose distribution to the target volume or organs at risk? In radiotherapy, things are more complicated. Geometrical quantities are not enough to evaluate the effect of AI-generated contours in treatment planning. To evaluate segmentation models that will be used in radiotherapy, we have to adopt a more comprehensive approach, the so-called QQD evaluation, which of course starts with the traditional way of evaluating segmentation models, but also includes two more steps: the qualitative evaluation, where a clinical expert reviews the segmentation in the patient's imaging data and decides if they can be used for further processing, and the very important dosimetric evaluation that helps us assess the effect of AI-generated contours in the dose distribution to the organs of interest. Let's analyze each part of this comprehensive evaluation. The first part, the quantitative evaluation, includes all the appropriate evaluation metrics. The dye similarity coefficient and Jacquard index calculate how well the predicted mask overlaps with the ground truth mask. The surface dyes calculates the boundary errors, as well as Hausdorff distance catches the worst boundary errors. The precision and recall help us assess how well the model can distinguish relevant from non-relevant structures. And the volume difference quantifies over and under segmentation, which is very important in the context of external beam radiotherapy. Regarding qualitative evaluation, a useful way of evaluating the clinical usability of contours is to adopt a Likert scale. In the literature, there are different scales for this task that range from 3-point to 5-point scales. Here we can see a 5-point scale proposed by Baruti and colleagues. In this scale, 1 is the worst case scenario in which the contour is unacceptable, while 5 means that the contour is clinically acceptable and it can be used as is. Moving on to the dosimetric evaluation of segmentation models, two questions arise. How do AI-generated contours affect the radiation dose distribution to the target volume and organs at risk? And of course, how can we assess the clinical importance of the differences between the AI-generated contours and the manual contours? Let's now see how we can implement a comprehensive dosimetric evaluation of segmentation models in practice. First, we create the treatment plan using the manually delineated contours. Of course, this will be done using the established guidelines for the specific disease and patient case. After that, we will calculate key dosimetric parameters, including target coverage, conformity, and dose to organs at risk. Then we have to repeat the entire planning process using the AI-generated contours now, applying the same planning objectives and constraints. Lastly, we recalculate the same dosimetric quantities and compare the impact of AI-driven contouring on dose distribution. A common methodological error that should be avoided is attempting to assess the effect of AI contours on dose distribution by simply overlaying the AI contours on the dose distribution derived from the plan that initially used the manual contours. We should keep in mind that in techniques such as VMAT, contours influence beam optimization and weight modulation. So the plan must be fully regenerated using the AI contours to ensure a valid comparison. If you want to take a deeper look on this comprehensive evaluation strategy, you can take a look in this recent paper which deploys a qualitative, quantitative and dosimetric evaluation in a machine learning model that used for segmentation purposes in treatment planning for gastric cancer. Thank you very much for your attention.
Thank you very much. Fantastic talks as always. Thank you. Our next speaker is Professor Michael Tzanis from the University of